there! In this short video, I will show you the derivation and proof of the law of cosines. Feel free to pause the video at any time, and away we go! Remember, one application of the law of cosines is to find a missing side of an oblique triangle when we're given two sides and their included angle. So, let's start with an oblique or non-right triangle. ABC, drawn in the coordinate plane so that one side, AB, lies along the x-axis. We'll place vertex A at the origin and vertex B at C0. The third vertex of the triangle, C, can be anywhere in the first quadrant, and its coordinates will be x, y. The side opposite angle A is A units, while side AC is B units. And side AB is C units. Next, we'll draw an altitude of this triangle from vertex C so that we can use right triangle trigonometry to represent angle A. Cosine of A is the ratio of x over b, and sine of A is y over b. Let's rearrange both of those equations to get x equals b times the cosine of A and y equals b times the sine of A. We'll set those equations aside for now and grab them in a few moments when we need them. Now, focus your attention on the smaller right triangle whose hypotenuse is length A. The vertical leg of this right triangle has a length of y, and the horizontal leg has a length of x minus c. Using the Pythagorean theorem, we can say a squared is equal to x minus c quantity squared plus y squared. Now it's time to use the sine and cosine equations we wrote a moment ago. Substitute b cosine of A for x and b sine of A for y to get a squared equals b cosine of A minus c squared plus b sine of A squared. Pause here if you need some time to verify what we've done so far. The rest of this proof relies on algebra and trig identities and not on the diagram. Let's remove it so that we have more room to work and focus on simplifying this equation. That's better. Remember, we left off here with an equation derived from the Pythagorean theorem and the sine and cosine ratios. Our next step is to expand each of these squared terms. Expanding the binomial gives us b squared times cosine squared A minus 2bc cosine A plus c squared. And squaring the sine term gives us b squared times sine squared A. Before I show you the next step, take a look at what we have so far. Are there any identities coming to mind that might help us simplify these terms? When I have squared terms, I usually keep an eye out for Pythagorean identities. Let's rearrange our terms to make it more obvious. Putting sine squared and cosine squared near each other gives me b squared times sine squared A plus b squared cosine squared A plus c squared minus 2bc cosine A. What do these first two terms have in common? When terms have common factors, what do? Right, we can factor out the b squared. And this part becomes sine squared A plus cosine squared A. And the Pythagorean identity tells us that this part is equal to 1. So the entire equation simplifies to a squared is equal to b squared plus c squared minus 2bc cosine A, which is the law of cosines, a formula that allows us to find the missing side in an oblique triangle when we know two sides and their included angle. If you're up for it, try recreating this proof using the other two angles of the triangle. Thanks for watching.